I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy, Haleakala Division. And one of the things that I get to do as part of my job is to put together these talks for everyone, and thank you all for coming and showing up online. This month's speaker is Dr. Jeff Kuhn, and I've known Jeff for, do we admit how long we've known each other? Okay. Since before either of us made our way to Hawaii. He got his undergraduate degree at Kalamazoo Community College. Kalamazoo College. Okay, Kalamazoo College. Good old Kazoo. And then went to Princeton, spent some time at Sac Peak, and Big Bear as well. Weren't you also at Big Bear?
I wouldn't admit it.
You wouldn't admit it. Okay, so he won't admit that. We'll skip over that. Found his way to Michigan State, and from Michigan State University, he was offered a position out here at the out in Hawaii, managing the Haleakala Division, and came out here. He's also a winner of the rather prestigious Humboldt Award, as well as a few others that I'm going to just gloss over. And he's going to be talking about Fermi's paradox, so a lot about searching for intelligent life, probably because we're having trouble finding it here. All right, with no further ado, here, let's give him a big Maui welcome, Jeff Kuhn.
Hi, everybody. So we don't have a speaker in the room. Can you hear me in the back? So shout at me if you can't when I wander off into. Steph, can I turn this light down up here? Does that work better? Okay, this was a cool image that I found on the web. It's the Earth at night, something which is relevant to what we're going to talk about today. And the reason why it was kind of cool, I thought, was because you could actually, in this satellite image, you could see part of the atmosphere above the lights, which are representative of civilization. And this is a picture that shows one of the things that I want to harp on a little bit later in this talk, which is that civilization is a very clustered thing, and the clustering of civilization is an important feature of what I want to tell you about today. So the question that we're going to talk about is where are alien civilizations? And it's a question that was, I think, in at least in the history books, posed first by a very famous physicist, Enrico Fermi, in about 1950, reputedly over, drinks at a bar. It wasn't in a published form, but what he asked was, and what he basically said was, given what we know about the size of the Milky Way, it's hard to understand how it is that there is no confirmed proof that extraterrestrial civilizations have ever made clear contact with us. And I'm going to address this. I'm sorry, it's going to be a little bit of a technical talk. So you're invited to throw stones or raise your hand or ask questions as we go. One of my colleagues today said that the aliens are already throwing stones at us with the asteroid and the meteorite. And actually, there was the Pan-STARRS folks said that there was a big meteor shower that was unannounced but quite visible last night, if you saw it, even a bolide that was visible in Maui. But what I'd like to do is revisit his problem, Fermi's paradox, with some modern technology and the understandings that we have today. And I'd like to say, first off, that we now know that there are lots of water-bearing Earth-like planets within communicable distances of the Earth, and that was something that was not known in Fermi's day, right? We now know there are lots and lots of extrasolar planets out there, and that's something that makes his paradox even more infamous. Why haven't we seen evidence of alien civilization is really a long-standing and unanswered question, and there's an active literature of people, lots of blogs. If you Google that question, you'll get an eyeful with lots and lots of views about why it is that we don't really have any confirmation. Some people will say that we do have confirmation, but it's my view, and I'll start with that we don't have confirmation of any kind of extraterrestrial presence in the universe. What we're going to talk about is what I call a thermodynamic extraterrestrial civilization marker or evidence. And there's some history to that goes back also to the heyday of the searches for extraterrestrial intelligence, which for us old-timers, you may remember, started in the 60s, soon after Fermi posed this question. And I'll try and review some of that history for you so you see where we're coming from. My final comment, and I'll provide some technical details to it, is that we do have the technology now for detecting an ETC. ETC is extraterrestrial civilization heat fingerprint. The heat fingerprint that we're after is related to global warming, and it's really this, what I mean by thermodynamic signature. So this is a roadmap for where we're headed. Let's look at where we are. We're out here somewhere. This is the Milky Way. The Milky Way is at most sort of 100,000 light years across. Okay, but we've been around, civilization has been around for what we could say the last 10,000 years. Homo sapiens have been around for probably 200,000 years. That's sufficient time for a light signal to go all the way across the Milky Way. How many stars are there in the Milky Way? Anybody know? Billions and billions. Lots and lots of them. And the fact that there are billions and billions, and in fact, if you draw a little circle, which is, say, 1,000 light years around where the Earth is, you'll run into millions and millions of stars. How can it be that within 1,000 years, and that's sort of what you might call modern civilization's time, no one has communicated with us? There is no evidence at all that there is any extraterrestrial civilization. Does it mean that life is so terribly unique and we were so special and lucky for it to happen here? Or does it mean that civilization, when it evolves, is very fragile and in almost all cases wipes itself out after some period of time? That question is a really interesting question. And if we had a way of answering it statistically from astronomical observations, that would be pretty cool. And that's the theme of my talk, that we actually do have a way, with some assumptions, of addressing that question. Is civilization something which, when it evolves, long-lived, or is it rare and fragile and not likely to take us further than where we are after roughly 1,000 years of modern technology, or somewhat modern technology? So the main point here is that the sun is neither particularly old nor young, and so civilizations live for thousands or millions of years. Why don't we see evidence of them? So the other theme to what I'm going to tell you is that we're not in a very special place. Right? You may know that in the history of astronomy, we once thought that we were at the center of the universe, or the center of the solar system, or the center of the galaxy, or otherwise in a very special place. And every time we learn more about our universe, it turns out we were wrong. We're not very special by any measures that we've been able to take. And so that's another theme of the talk, which I think is going to guide the assumptions that go into the argument I'm going to present to you. This is much more technical than you need to worry about. What it is a plot from the most successful extrasolar planet hunter that man has ever developed. It's called the Kepler Mission. It's still working. It's up there looking for planets that pass in front of their star. When they do, the star gets a little bit fainter, and you go back and we have evidence of planets by looking at that dimming. Kepler has found thousands of such planets, and this is just a plot that I wanted to show you. It's hard to see. It shows that, and so this scale right here on the left shows the size of the planets from sort of, here's an Earth size upwards, and these lines right here show where the experiment doesn't have any sensitivity. And each one of these crosses is a measurement, and what it shows is where there's sensitivity, Kepler is finding lots and lots of planets, but they're all bigger than the Earth. You could imagine if we had sensitivity down here, there would be even more, because we happen to know that the Earth is a planet, and it's at the edge of the sensitivity of the Kepler mission. So remember these numbers. It seems like 30% of all solar-like stars have habitable zone terrestrial planets. What does that mean? Thank you, Stan. These are stars that are sort of like the sun. This means this is a symbol that shows the temperature of the star. F means it's slightly warmer than the sun. G is a star which is about 10,000 degrees. That's how hot the surface of our sun is, and K means it's a little bit cooler than that. So of those stars that are like the sun, you can say by all of our predictions, although notice here, we don't really know what's going on down here, 30% of those stars have planets in the habitable zone. Anybody know what that means? Habitable zone? Not too hot, not too cold. It means that water could exist, liquid water could exist on the surface of the planet. And that's good if we believe that we're looking for life that might have some similarity to us, and therefore we might have some ability to learn or communicate with them. That's not to say that there isn't life in all other forms and all other planets, but let's restrict our attention to those planets which are likely to have liquid water and for which we have a hope of likely communicating, maybe understanding, maybe learning. I should also say that the other number which is important as we get into this is the number of stars, which are brighter than, astronomers use these magnitude limits, and 13th magnitude is fairly bright. The number of stars that are brighter than 13th magnitude within 60 light years of the sun, which is sort of a benchmark distance out that I'm going to be concerned with. 60 light years means if we found a civilization, our grandchildren would be able to hear the answer to a signal that we might send to them. So let's call that the communicable distance, right? Because we've got to send the signal out and it's got to come back to us. So I think that's an interesting radius. This turns out to be an interesting brightness for what I'll show you. And there are something like 600 stars that meet that criterion. And so the other message from this slide is that planets are about, or perhaps even more, common than stars. So when you look out and you see all those stars, think and recognize that there are probably just as many planets, because a lot of the planets, a lot of the stars have multiple planets around them. Maybe that's not too surprising. When the universe was formed, we formed planets and stars, maybe with not such an unequal frequency. Perhaps not too surprising. Okay, planets are a common thing. This is all news. When I learned astronomy, we didn't have a clue that there were extrasolar planets. We in fact thought that the Earth was rather special. Many of us did that were trained in astronomy. Okay, so let's do something like, some of you may have heard of the Drake equation. Back in 1960, Frank Drake, who was an astronomer, laid out what he thought were all the terms, all the things that we had to know to estimate whether or not there would be extraterrestrial civilizations. This is a Drake-like equation, but I'm gonna phrase it in my own language, and it's based on thinking this way. So this red line, think of as a timeline. So here we are, and here alien civilizations are. At some point in time, we're going to have the technology to detect alien civilizations. An interesting quantity, an interesting fact, is whether or not an alien civilization starts producing a signal, and I'll describe what that signal is in a minute, before or after we turn on our ability to see them. Okay? But in general, let's imagine and let's define a successful civilization as one which somehow becomes visible at some point in their development. And if they're successful, they're going to be visible, as I'll show in a bit, throughout their history. An unsuccessful civilization is one which either never gets to this point or gets to this point and then clicks off because bad things happen. We can imagine that we are very close to a limit where as I'll show you in a bit, our planet could be detected nearby or not too far away. Okay, so how many detectable extraterrestrial civilizations are there? Well, that depends on the number of stars. So let's take the number of stars in this communicable radius, and I've already told you that number is like 600. Let's take the fraction with planets, all right? And we already know that fraction with planets is really, if we included all the ones that are smaller than 2 or 3 Earth radii, is a number which is, let's call it a half. How many planets are in a habitable zone for those? And I put in another number here, which is something like a half. Okay, so we're running through all the probabilities that give us a detectable civilization. What are the fraction that develop a civilization? Well, now I want to appeal to what I said earlier. We're not very special. There's no evidence from anything that we've ever measured astronomically that the Earth or terrestrial life is very special. So I want to put a number of a half in there. It's a number which is halfway between 1, a certainty, and 0, it never happens. So let's call it a half. The fraction that warm up, because we're going to be talking about a global warming signature, before the Earth develops its detection strategy, is another important number. And what number should we put in there? A half. What a great idea. A half. Here's the number that we want to know. What's the fraction of all of these that are successful? That's something we have no idea about. Fermi would say, perhaps, civilization is not a very robust thing when it happens. It dies out, and that's why we never have any contact. Now, there's another hypothesis, which is, if you were a civilization on another planet, would you advertise your existence? Maybe not. We learn from evolution and the competitive universe that we live on here on the Earth that if you do that too much, you're going to get eaten. We don't really want to be eaten, and so it may well be that civilization, so this sort of approach we've taken to finding extraterrestrial civilization by looking at beacons that they send to us is just the wrong idea. On the other hand, it may be possible, as I'll show you, that we can see civilizations that don't want to be seen, that there's a natural signature that we can look for, which is something that we can actually begin to think about doing now. So this is the number that I'd like to know. We'd like to know, is there a likelihood that civilization, when it clicks on, survives for a long time, or is it fragile and it clicks off? What fraction of civilizations that make it to this point actually continue on? I'm going to argue with you today that we can learn that number. We have the technology to do that. Okay, so suppose we could detect ETCs. So I just put those numbers down. Fs is what we want to know, the probability that civilization survives. So if I take those numbers, the number of detectable civilizations in that radius is 38 times whatever that fraction is. Well, if the fraction is a half, then we ought to be able to detect a significant number. And if we somehow mess up and our estimates are wrong, that number is big enough that we can do it. That's a really big number, 38 there. And so Fs, even if it's a relatively small number, the survival rate of civilizations, we ought to be able to see it. So my point is that the Fermi paradox is really a very pervasive and interesting question when we consider that we now have the technology to be able to show that civilization is either a very rare and fragile thing or robust. We just have to be able to do this. And I'm going to show you how we do it. Another way of looking at this is that about 7% of the number of stars times whatever this fraction is should be detectable. And I'm going to tell you what detectable means. Okay, so let me give you some background to the search for extraterrestrial intelligence. My sense of this is that we really should be talking about searches for extraterrestrial civilization. I don't know what intelligence is, but it's extraterrestrial civilization that we're after. Okay? The search for extraterrestrial intelligence goes back to the 1950s and the 60s. And it was a huge effort by many reputable scientists back then, only 50 or 60 years ago. Fermi, as I said, started us off with this question: why is it that we don't detect anybody when we should? Caccioni and Morrison published a very influential paper in the magazine Nature in 1959, where they suggested that, hey, radio telescopes have some sensitivity. If a civilization wanted to communicate with us, we ought to be able to train our radio telescopes at wavelengths of 21 centimeters, which has a special meaning for astronomy, and find signals. And I would say that this launched, really, the notion that we could possibly detect alien intelligence if that alien intelligence wanted to communicate with us. In 1960, in the magazine Science, Dyson published a very interesting paper that said, well, some civilizations we can detect even if they don't want to be detected, and this is the germ of the idea that we're going to pick up on. Frank Drake, who I just mentioned his Drake equation, launched the first, I think, very serious radio survey back in 1961. The Russians were really big. It wasn't just a U.S. thing. The Russians, in fact, probably launched a lot of the activities related to this question. Kardashev, in 1964, he's still around in his 80s, argued that we can think of civilization in three different types, and I'm going to appeal to this as a germ of another idea we're going to pick up on. And then and Sagan in 1966 published a very influential book called Intelligent Life in the Universe at Wyshlovsky that published it in the Soviet Union, and Sagan adapted it, Wyshlovsky, for the English press. That was very influential, and I'll refer to that. Okay, so let's go through some of that history quickly. Ciccione and Morrison, in the background is Phil Morrison looking back at you, said, it is reasonable to expect that sensitive receivers for this frequency will be made at an early stage of the development of radio astronomy. That would be the expectation of operators of the assumed source, the aliens. And the present state of terrestrial instruments indeed justifies the expectation. So what he said was, based on us, others are likely to be able to signal to us at this special frequency. Of course, it depends on the argument that you want to be found, and this is my problem with the premise of all of these SETI searches. I think there's a natural sense that life doesn't necessarily want to be found. There's a debate in the community, exobiology community now, about should we be broadcasting signals out to nearby stars announcing our presence, and that's a legitimate debate. So you may not know that the National Radio Astronomy Observatory was almost formed because of this search for extraterrestrial intelligence. Frank Drake at the NRIO in Greenback, West Virginia, that was one of the first projects. This telescope, which has since collapsed to the ground, but this telescope was used to work on, was a search for radio beacons from nearby stars that could be identified as intelligence. Within the conventional SETI community, the most sensitive search has been the Phoenix Project, which used a large number of radio telescopes and looked selectively at 800 stars. It had the sensitivity. If we had taken our most intense military radar and beamed it at the Earth from these stars, there was a possibility of detecting the signal. The only problem was each one of these stars had effectively 6 minutes of search time in each frequency band that it might have been beamed at us. So it's a needle in a haystack, and this was discontinued in 2004. The search for extraterrestrial intelligence is one of the most well-funded problems in astronomy, but not by the government, at least not after the late 1990s, when Proxmire and others said, we're not funding searches for little green men, and all NASA funding for SETI was cut off. Since then, tens of millions of dollars of private money has gone into this, and you may know that Alan of Microsoft has funded one of the most powerful radio telescopes, which is being used for other purposes now, but it was used to continue the Phoenix search effectively. I'm going to talk to you about not radio searches and not searches for beamed signals. There have been other searches that suggested that maybe aliens would be shooting laser beams across the universe and one might just intercept us. And if you had a small telescope and you trained it out at stars, you might suddenly see a bright flash which could be what's called SETI. And there are a couple of efforts that go on now on that. But these all assume these are civilizations that want to be detected by sending their beams. Okay, so Dyson was the first one to enunciate this idea that I want to expand on. What Freeman Dyson said in 1960 was, okay, if I'm an alien civilization, it's very likely that I'm going to need power, and the best way for us to get power is to capture all of the energy from our star. And so he suggested, let's take, in our case, suppose Jupiter. Let's take Jupiter, construct a bunch of nanobots, here's the sun, and construct a structure that absorbs all of the energy from the star. Now we can use it for our own purposes. What happens to all that energy, though, after we use it? What's it converted to? It's converted to heat. And so he was the first to say, well, okay, if we took all of the energy of a star and converted it into heat energy, we have a chance, and this was back in 1960, it wasn't actually true in 1960, but there was an opportunity possibly to look for objects in the universe that only had heat energy and no optical energy. That was his idea. And this was called a Dyson Sphere. There are a lot of people that have written about it, and if you go to the web and Google on it, you'll see that it's an idea that many people have thought about. How would we do that? It's not clear how we would do that, but if you're a very advanced civilization, you might. Astronomers have looked for this signal. There's a nice paper in 2009 where the infrared astronomical survey, IRAS, was mined to find anything that had only heat energy and no optical signal, and nothing was found. Okay, so this comes up blank. Kardashev, and that's him staring back out at us, argued in 1964 from the Soviet Union that the transmission of information by extraterrestrial civilizations might be something that we could gauge if we characterized extraterrestrial civilizations into three categories. And what he said was the following, that Earth is a type 1 civilization because we use much less than the power produced by the star, our star. Right? A type 2 civilization uses substantially all of a host star's power for civilization's purposes. So Dyson civilizations would be type 2s, right? Fairly advanced, right? And able to take a planet and take it apart and build a screen around your star, something that's not easy to do. Clearly much more advanced than we are, but not physically, not fundamentally impossible. He went on to say that, well, type 3s can use the power of their entire galaxy. And he went on to say that such a civilization is probably not distinguishable from God, but let's imagine this, because you can imagine astronomical searches for such civilizations. For example, some people have speculated that quasars, which are as powerful as entire galaxies in terms of the amount of energy that they release, maybe they're really type 3 civilizations, and we're just seeing their waste energy for some reason. I'm not sure that we take those seriously. We have physical models that would seem to explain them, but it's an interesting way of thinking of the development of civilization, and it's important to what I'm going to tell you, which is that let's think about the advancement of civilization in terms of the energy or the power that it uses, the energy per time. One more step in this history was Shklovsky and Sagan argued that, well, we could actually parameterize that. We could assign a number to a civilization as the log base 10 of the power, measured in watts, divided by 10 minus 0.6. I don't know why the 0.6 is there, but in that case, the Earth, which is now consuming about 15 terawatts of power, has K equals 0.7 on the Shklovsky and Sagan scale of power use. And it's an interesting idea to say that civilization advances, and as it advances, it uses more power. Let's think about that just a little bit. You might argue that civilization doesn't naturally have to do that, but I'm going to argue in a minute that it does. And something we need to understand is that I want to look for type 1 civilizations, civilizations not so different than the Earth, because presumably they're much more common than these rare and powerful godlike type 2s or type 3s, which we've looked for and we haven't been able to find. And they're so far from our understanding, it's pure speculation about what they might be or might do. Okay, The Earth orbits the sun, and the temperature of the Earth is a fundamental property of the Earth. You could compute the temperature of the Earth if you knew how bright the sun was and you knew how far away the Earth was from the sun. And you get the temperature by balancing the total amount of power that the sun produces that's absorbed by the Earth by the amount of heat that the Earth radiates. Okay? So the Earth is basically a converter. It takes mostly the optical power from the sun and converts it into heat, which radiates in the infrared. Okay, so it takes visible light energy, converts it into heat energy. But the total amount of energy coming in is equal to the total amount of energy going out. Right? And the temperature of the Earth adjusts itself to make that true. There are lots of other details, like how much energy is reflected, that's called the albedo, and how much energy is trapped by the atmosphere of the Earth and things like greenhouse gases. But basically, our planet absorbs energy and then radiates it away. Okay, why is that important? Well, so this is Freeman Dyson staring back at us. The Dyson Sphere is a Kardashev Type II thermodynamically unavoidable but perhaps too advanced example of an ETC. Right? It's unavoidable in the sense that as we use the power, we create heat, and we can't avoid that. The laws of thermodynamics don't allow us to hide that heat. It will be radiated away from the planet no matter what we do. We could bury it in the interior of the planet for a while, but as the Earth heats up, that will eventually be radiated. Advanced civilizations use power, and they must produce heat, okay? That's what we're going to talk about. Most of an ETC's power is eventually converted into thermal radiation. I say most because we do have lights, and lights produce a little bit of energy that's radiated away as light. So I showed you that first slide of Egypt, and that's a little bit of power. It's nothing compared to the heat power, though. Here's what I'd like to do. I'd like to define a number that doesn't have any units. We say it's dimensionless, which is the power used globally. So that's in terawatts, or it's in watts. It's energy per second. That's the energy that our entire civilization consumes. And I want to normalize it. I want to divide by the power that the Earth intercepts in sunlight. Okay? So right now, we're producing power from all of the coal stations and the nuclear stations and the windmills all over the world. And do you have any idea what fraction that power is compared to the total amount of power that the Earth intercepts from the sun? Any guesses? Stan says it's a billionth, which is 10 to the minus 9, right? Any other guesses? There's no wrong answer. Well, there is, but I mean, it's okay. There's no grade. It's a surprisingly large number. And the other point that I want to make is that no matter what we do, if you believe that an advanced civilization is all about accumulating information, storing it, retrieving it, making new theories, keeping data for tax purposes, whatever it is, that information requires energy. Okay? And we're going to approach a time where most of our energy and power utilization is going to go towards data manipulation. And there are actually thermodynamic arguments that show that at some point the manipulation of raw bits takes more energy than anything else when you have enough of those raw bits. Okay. So here's my omega scale. I'm going to postulate that as others have, that as civilization evolves, we move to the right on the scale. And this is a scale, and we say logarithmic units. Here's 10 to the minus 7, so Stan's number was 10 to the minus 9 way down here. The present global power production is right here. It's larger than a 100th of a percent. we are already using 0.04% of the total power that the Earth absorbs from the sun. That's okay. Okay. You're right. That's a tinier number. But compared to the total omega, we're going to normalize because that's a good number to the total power that the Earth absorbs. Because remember, when the total power that the Earth absorbs is responsible for giving us the temperature that we now have, right? The comfortable room temperature that exists on Maui is a consequence of the fact that the Earth is absorbing a lot of power. Okay, some other numbers here that I think are interesting. During the Roman period, global power production, which you can imagine is mostly campfires, was 10 to the minus 7. And since gotten up to 4 times 10 to the minus 4. If we just included the biological heat production, so I mentioned that because you remember the movie Matrix. The power source in the movie Matrix were human beings connected to the pod that were metabolizing whatever they were metabolizing. That power source is 3 times 10 to the minus 5 on this scale. The present global optical power production is down here compared to the total power production. So this is what I was saying. This is the light which is radiated up into space, and it's quite a bit less than the total power that we're using. Less than 1/10 of our total power. If you took all the power of all the plants converting carbon dioxide and sunlight into oxygen and digestible materials, which basically fuels our entire food chain, that's only a little bit larger than this number. It's a few tenths of a percent of the total sunlight that strikes us. Okay? So what must happen as we approach 1? Well, we said that all of this power is reintroduced into the environment of the planet. This is a real global warming problem, right? We're already to the point where 0.04% of the total energy that goes to heat the planet is coming from us and our power consumption. We can't do anything about that. As we consume more power, we produce more heat, and we're at the point where 0.04% of the sun's total power is going to heat the planet. As we advance, that number will go up. That global heating becomes something that is going to make us uncomfortably warm. Yes? You'd have to add those together, but that's so much smaller than this number that it's not a very big effect. So the noise in my estimate of the global power production is like that, and we wouldn't notice the human production. Yeah. You get the prize. So an intelligent civilization is going to power itself with photonic power, with the oil that was produced by earlier photosynthetic global power consumption, right? And that doesn't affect the energy budget. So the best way for civilization to avoid this fundamental global warming problem is to use solar power, right? And the best civilization will use the power, reintroduce the heat back to the planet to keep the planet toasty warm for us. And it won't break the bank in this budget that heats the earth. And in fact, that's likely what happens to civilizations. You don't have to read all this. This just says that information costs energy. Information costs power. And it turns out that if you took all of the stored digital information right now, it's 3 times 10 to the 20 bytes. Well, that was when I looked it up few months ago. The doubling time is only 2 years. So every 2 years, this number doubles. That's actually quite a bit faster than the increase of global power consumption, which is going up at a rate of 2.5% per year. So our power consumption, of course, continues to rise, but only at a rate of 2.5% per year. Could this just be due to population increase? No. The population increase is now less than half of this number. So population increase is only about 1.3% per year. So that's all of our cell phones, computers, digital networks, and the increasing reliance on the global power. But this is a smaller growth rate. This is a huge growth rate, right? And it's not likely to stop. We consider the advancement of civilization related to the amount of information that we're able to use. And there is a waterfall, a flood approaching us associated with that information and how we're going to power that and use it. So here's the point that we just made. Photonic power provides both heating and the largest useful planetary power. It implies a low planetary albedo and a large thermal to visible radiative excess. So it's kind of this idea that Dyson made for an entire star, that if you wanted to look for an extraterrestrial civilization, which was advanced, what you should do is look for a civilization which has a lot of thermal energy radiated, associated with the civilization, and not much optical energy, because that's the reflected starlight, and they'd be capturing all that starlight to power their cell phones and heat their planet all at the same time. There's some more details that talk about laws of physics and heat. The likely thing, the best way of using that power from the star is to reintroduce the heat at the temperature of the planet. That's the most efficient way of doing that. Civilizations will evolve from omega less than 1 towards omega equals 1. They won't go beyond omega equals 1 because it's uncomfortably warm. So there's an accumulation point, omega equals 1, for extraterrestrial civilization, and we ought to be able to look for it. The longer a civilization survives, the closer it gets to 1, we could imagine. So there's our prescription for looking for ETCs. This is a completely unintentional and something that couldn't be hidden by a civilization. Okay, so how do we do that? I just wanted to show you that we're already producing a lot of heat on the Earth. This is a satellite image that shows Paris. Here's a temperature, this is the Celsius scale, so it's sort of 5 degrees of excess heat which is produced by the civilization. It also shows the point that I think is important for civilizations, that signals associated with civilization, these are optical signals, but they might also be heat signals. Civilization is clustered, and it really has to be, right? If only because of the geography of the planet, but also because the most efficient way of producing food and putting people together is to cluster them. It won't be distributed uniformly, and that's an important feature to how we're going to look for this signal in extrasolar planets. So you might imagine then that the civilization fingerprints we're after are to use the planetary reflectivity and the planet temperature and emissivity to give us a fingerprint for extraterrestrial civilization. So that's what this is about. Can we detect civilization by looking at the optical and the infrared signals that come from extrasolar planets? Here's an artist's rendition of, here's a planet which is not in the habitable zone. Look at how bright it is as it reflects light. It's too close to this star, and that's why it has this bright phase to it. Here's a planet which is in the habitable zone with an omega close to 1 civilization on it. Here's the clustered civilization on it. We see a little bit of the bright side of the planet because the atmosphere that we can't avoid scatters some light. And so that scattered light out of the atmosphere we'd be able to see, potentially, as we looked from a distant vantage point. But the thermal emission from this planet would be a much more important and telltale signature. So if we could look at individual planets in the infrared and the visible, this one would stand out because it would be bright in the infrared but dark in the visible. Okay, so I was going to get into some technical details. I'm going to skip over this pretty fast, except to say that astronomers now look for this idea of hot spots and cold spots on other stars already. You know what they're looking for? Star spots. It's like the sunspots we have on the sun. So astronomers have developed techniques to see small, dark, and bright features on other stars. And you know how they do it? They use the rotation of the star to bring things around in view, and then by looking at how the brightness changes in time, we can see things that are much smaller than we would normally be able to see. That's the same idea that Kepler uses to find planets, right? Kepler doesn't have the ability to see an individual planet. But what it does see is as a planet rotates across the face of the star, it sees the star get a little bit fainter. So that's the idea that we're going to use to detect signals from extrasolar terrestrial civilizations. And this isn't too important, except it does show you how the technology works. So imagine we're looking from a long way off. We have a really cool telescope that allows us to actually separate the planet from the star. So if we're looking from this vantage point, when the planet is behind the star, we see a peak in the brightness. And so the visible light will be peaked because we're looking at the bright side. And when it's over here, it'll be dark. Okay? But the planet also rotates. It doesn't just orbit around the star, but it also rotates. And it's that rotation that brings elements of that clustered civilization in and out of view that we can look for as evidence of civilization. And so I've indicated that here. These curves are a simulated, it's really a reflectivity variation. And in the infrared, there's not much variation at all, right? The visible goes from high to low because it's basically dark here. But in the infrared, the whole planet is radiating, right? So even when you look at the dark side, you're getting that thermal energy. So it's a much smaller signal. And the signal that I've introduced in here, which is the civilization signal, I've ginned up a computer program that can look for, it's called a blind detection of civilization. And this is what I put in, this signal right here, and this is what I recovered. And the slide is supposed to show you that even a civilization that has omega equals 0.01, so this 0.01 scale here means that this is a civilization which is using power at the 1% level of the total power from its star that's illuminating it. So even at the 1% level, we can detect omega equals 0.01 civilizations with this sort of technology. Okay? And it uses this fact that we don't and we won't for many generations have telescopes that can resolve a picture of a star like this. We're never going to have in ours or yours or your children's lifetimes a telescope that can see a picture like that. But we will have telescopes that can separate the light of the planet from the light of the star. Okay. This is called a blind reconstruction algorithm. It uses these tricks. So by looking in the visible and in the infrared, we can extract the signal at a weak level. Those are details. The question that we have to ask now, so I'm working up to the point of trying to convince you that we could go off and do this problem now to look for civilizations. The first question that you have to ask, though, is how bright is a planet compared to the star? Do you know the answer to that? What does it depend on? Well, the bigger the planet, the more energy it's going to radiate in the infrared, or the more energy it will reflect from the star, right? If the planet were as big as the star and nearby, it would reflect almost as much light as the star produces. But planets are a whole lot smaller. And so this is a set of graphs that shows the ratio of the amount of energy the star produces divided into the amount of energy that the planet reflects back to us or radiates to us in the infrared. Okay, so on this axis, I apologize, it's a little complicated, but it's an important detail of how this works. Here's the temperature of stars, and these are measured in degrees Celsius, or Kelvin. Here's a very cool star that's 2,000 degrees. Here's a very hot star that's 12,000 degrees. Here's the sun right here at 6,000. As the star gets hotter, what happens to the habitable zone? Does it move further away or closer? It moves further away, right? You've got to be further away from something really hot in order to have water, liquid water, at less than 100 degrees Celsius. So that means a planet in the habitable zone around a bright star is a lot further away. Is that going to be brighter or fainter than a planet which is close to its star? It's going to be fainter. And that's why, as we go to hotter stars, this ratio of brightness, the planet brightness, gets smaller. Okay? So these curves represent different wavelengths and different sizes for a planet. So look at the red curve. The red curve is for a planet which is the size of the Earth. The dotted curves all represent planets that are 5 times the Earth diameter. And of course, they have more energy, right? By a factor of how much? It's the area of the planet, it's 25 times, 5 squared. So a planet which is 5 times larger will radiate. The ratio of its brightness to the brightness of the star is sort of 10 to the minus 4. So that's 1/10,000th, declining to, that's about 1/millionth. That's at a wavelength of 10 microns. So what this is saying is that if you want to look for planets, what's the best wavelength to look in if you're worried about the contrast between a bright star real close to your planet? You want to go to long wavelengths, that's this red curve, and you want to look at stars that tend to be cooler. And so what I've done is fold this information into everything we know about those 600 stars to tell you how many planets we could detect based on these conditions. Okay? All right, but I have to tell you more. Sorry, it's not an easy story, but it's a good one. So the habitable zone liquid water planets are more easily detected around late type. Late type is an astronomer's jingo for cooler stars. But the star-planet separation in this case is smaller. Well, here's our problem. Planets are not very far away from stars, especially when you put them many light years away. And current telescopes are just barely able to separate the planet from the stars. To detect a star with a telescope means to be able to see a very tiny angular separation. So many of you may have telescopes. If you want to find small separations, what do you have to do? You've got to have a bigger diameter telescope, or you've got to get outside the atmosphere. And if you're using a bigger diameter, you have to use adaptive optics anyway. So you've got to correct for the atmosphere, whatever we do. So to measure these small separations on these planets that are close to cooler stars requires a really big telescope. Okay? And it turns out that the separation of the planet from its star divided by the distance to the star, that's really what we would call an angle, is proportional to the wavelength that we're looking at divided by the diameter, the size of the mirror in the telescope. So if these two things have to be comparable, d is the distance to the distance from us to the star. How are little d and big D related? They have to be proportional, right? They both appear in the denominator of this relationship. So a bigger diameter telescope can see planets further away. Right? Okay, so how many planets or how many stars on average will we see as we go to a further distance? Well, if I double the distance, how many more planets would you expect to be able to detect? It's the volume that we can see to, right? So the volume of, think of a sphere surrounding the sun, double the radius of that ball, and the volume goes up like the radius cubed. So you double the size of the telescope, and the number of planets that you can see goes up by 8 times. It's a huge factor. This is an example of a problem that fundamentally depends on big telescopes. I'm going to show you that in a minute. That's what this says. So we have to come up with a telescope design which has, we say, a large aperture. It's a big diameter. We're going to look in the infrared, and so our telescope has to be good at measuring infrared signals. Well, we're embedded in this region also at 288 degrees Kelvin, and so we have to have a telescope that astronomers say has low emissivity. Even more important is this telescope, unlike any telescope that exists now, has to be very good at separating this bright light of the star from the very faint light of the planet. And that requires 2 things that astronomers call adaptive optics and a coronagraph. So those are special features, and I won't say too much more about it, but I'll show you some examples. Can we do this problem with the world's largest telescope? This is Keck, so it's our neighbor. This is the world's largest telescope. Here's the primary mirror. It's about, about 10 meters across. This telescope, by far, is not big enough, and it scatters too much light. The light from a star gets spread out over our image, and it completely obscures our ability to see faint things. And this is the problem, right? With a dirty windshield, you can't see a driver in an incoming car. The scattered light in this picture is such that this is our problem. We have a really, really bright star that could be millions of times brighter than the planet, and we want to find the light from the planet. That's our dilemma. Don't tell the Keck people what I'm showing you. This is a picture of the deformities in the Keck primary mirror, and they all contribute to scattered light. This is what the image of a bright star looks like in Keck. So the Keck is a whole bunch of mirror segments. Is it 35? 27? I've forgotten. You could count them there. Each one of them is a hexagon, and they're packed close together. The scattered light from all of the edges in those mirrors produces a profile which just looks horrible. Imagine trying to find a planet 1,000,000 times fainter than the brightness of the star. And you can subtract away all that structure, and you're still left with something which is just impossible. The modern telescopes that we're talking about building have scattered light that's not going to let us do this problem. And there are 3 of those modern telescopes that are being considered. The giant Magellan telescope is close to being able to do this problem. It has 3 very nice mirrors that are as big as we can make them. The ratio of the edge to the area of the mirror is what determines how much light is scattered. This is a good one. The extreme European Large Telescope, the European Extremely Large Telescope, is 44 meters across. The mirror segments are actually smaller than Keck. The TMT, which we're debating putting here in Hawaii, is slightly smaller than this. It's 30 meters across. It's about 400 mirrors that are all smaller than the Keck telescope. Those mirrors, if you were to draw them, look something like this. And that's a horrible thing to use to try to look for extrasolar planets. So these telescopes aren't going to do it for us. If we go back to that list of all those stars that are nearby and we ask ourselves the question, just based on the size of the telescope, how many extrasolar civilizations could we detect that, say, had omega equals 1? So here's the diameter of the telescope. this is the detectable number of planets that are Earth size. Here's the GMT, the TMT, the EELT. Here it is at close to 40 meters. It's 39 meters now. The TMT is 30 meters. The GMT is 23 meters. The different curves here correspond to a different assumption about the coronagraph that gets added to the telescope. So how good is it at removing scattered light? And these are all basically perfect. The answer is that the most we could ever detect with the EELT, if it's ever built, with the most optimistic machine called a coronagraph, is maybe 10 or 12 extraterrestrial systems where omega was equal to 1. That's not going to work. We'd have to be phenomenally lucky to be able to find something interesting. It does get interesting if we could go up to a telescope that's about 70 meters in size, and now with a telescope designed for removing scattered light, up close to a bigger than the Earth diameter. If you double the size of the Earth, it goes up to several hundred out of those 600 stars. That's where we want to be. That's what we want to build. Okay. I'm going to show you what it looks like. That's the cracked glass telescope. So, is it possible to build a telescope which is basically the size of a football field? The reason why telescopes are hard is because we have to be able to support the mirrors in all of these other telescope designs to better than 1/millionth of a meter. 1/millionth of a meter, much less than 10,000ths of an inch. And over a structure that's the size of a football field, you can't make it stiff enough. But let's relax the assumptions. All of those 3 telescopes that astronomers have been debating building for the last decade rely on satisfying a large community of astronomers that have many different pet problems. That telescope is required to have a large field of view. What we mean by that is it has to be able to see many stars at once. It has to be used to go out and look at galaxies. So it has to work under conditions that turn out to be very difficult to impose. Suppose our telescope is only going to look at one star at a time, and that star is very bright. So the field of view of our telescope can be almost 1/millionth less than the field of view of all these other telescopes. That makes it a very different problem. What if we made the telescope a whole bunch of telescopes that we already know how to build? The Keck telescope and the Subaru telescope and the Gemini telescope over on the Big Island all use mirrors that are about 8 meters across. Suppose we could efficiently make lots of 8-meter mirrors. Could we make a big telescope out of those building blocks? If we do, we have to get around this mechanical problem that we can't build a structure that's stiff enough to hold things together to 1/millionth of a meter. So we've got to solve that problem. Well, about a year and a half ago, we found people crazy enough to sign up to do this. We formed what's called the Colossus Corporation. The Colossus Corporation has some reputable people in it. I'm not one of them. A wealthy venture capital person is funding the operation. The man who started the company which built the Keck telescopes and many of the world's largest telescopes is a founding member of the Colossus Corporation. Some very reputable astronomers, some of them in this room, I won't tell you who they are, they don't want to be identified, are involved in this. And actually many people within this technology of doing optics are part of this endeavor to prove that it's possible to solve this problem and actually build a telescope which is 77 meters across. Stan doesn't want to be identified either. So the telescope concept looks like this. So it's an array. Each one of those is 8 meters across. This is Doable because it's not a wide field telescope. It uses the star itself, which is the host star of the extraterrestrial civilization on a planet around the star, to define how each one of those mirrors is positioned with respect to the other one. It doesn't depend on the mechanical structure or the mirror next to it. It's not a cosmology telescope. And it's probably also not a national telescope from any particular nation. You may know that all of the world's largest telescopes were not built by astronomers, and they weren't built by your tax dollars. The world's largest telescopes, going back 150 years, were all built by private money or foundations. And that, in fact, is the approach that the Colossus Foundation is taking in showing that this telescope can be built. This is the optical structure. Each one of those is 8 meters across. What makes it very interesting is each one of these sends light to one of these. That's a secondary mirror. And the focus of the telescope is up here about, so this is 70 meters across. This is about 30 meters up. So it's a fairly simple mechanical structure, as you saw from before. There's a tower that comes up to here. Each one of those secondary mirrors, by design, isn't very big. It's only about this big across. And it's the combination of this optics and each one of those that allows the telescope to work. It's constantly working to look at the star and adjusting the position of all of those optics in a very dynamic and electronic way. The mechanical structure has been designed. We know that we can make it. The mass is enormous, but it's something which is much less than the mass of these other telescopes that are less than a half the diameter of this one. The final configuration has a mirror and a secondary, and then all the instrumentation lives down here at the plane of this. It's a parabola. It forms a parabola here at the base of the telescope. A lot of work has been done to understand what the atmosphere does over these very large distances. The atmosphere introduces errors into the image that all have to be corrected. And those errors are correctable using some algorithms and technology that is being developed here. The end product of all of that is that we can produce, so this is a kind of a surface plot that shows how sharp an image of a star would be. And a star would be very sharp, and it's only, so in astronomers' terms, it's hundredths or thousandths of an arc second across. That's so sharp that we could see a little bump over here, which is a planet. We could separate the planet from the starlight using this technology. These little bumps here are related to the fact that our mirror consists of a bunch of separate mirrors. So in answer to your question, those 60 mirrors are pretty close together, but not packed right up against one another. And that fact means that we get a few little bumps over here that we might confuse for stars, but they're in fact small enough that we can separate them from the light that we would get from an extrasolar civilization nearby. So that's pretty much all I had to say. I think the take-home messages are advanced civilizations will be limited by real global warming, not the global warming associated with changes in the albedo or the CO2 content in the Earth's atmosphere. Fundamentally, our power consumption is approaching a point where the planet will warm, and that's something that's not avoidable. Global heat is observable with somewhat larger terrestrial telescopes than we are now planning. But those telescopes are buildable with current technology. There's a corporation which is formed to do that and make that even demonstrate that. And ETC census is really what we want to do. We want to take the nearest stars, do a census of the civilizations that are there, and by knowing how many signs of extraterrestrial civilization we detect, we have this chance of answering the question, is civilization a very fragile thing? Suppose we do this census and we don't find any evidence of civilization. That's the bad news, right? but it might be sobering enough that we could actually change what we're doing. Who knows? The final word, I think, is that it is possible now to build such a telescope, and there's a fairly serious group of folks that are involved in trying to prove that. Okay? So that's it. Yeah. So the question was, when could we build the Colossus? The group which is engaged in demonstrating the technology now, which involved a bunch of private investors and some physicists and scientists, many from here at the IFA, believe that this is a telescope that we could put on the sky in 5 years. It's really revolutionary technology. It doesn't depend on the kind of polishing, for example, that went into building all of the 8-meter telescopes that are over in Mauna Kea. There's some fairly, I will say, very new ideas that are going into how we would make mirrors that do that. And the 5-year window is the window that has been established. There are demonstration projects that are going on now. The gentleman sitting next to you is Professor Akano, who is from Japan, and his telescope, which we're building on Haleakala, demonstrates a lot of this thin mirror technology that would go into this. So there are a series of steps, but all of us involved in the Colossus Corporation now believe that it's the sort of thing that with the proper private money, we would build within 5 years. Yeah. It's a combination of the thermal footprint and the visible footprint. Yes. So we need to be able to, and I'll tell you why. You might imagine, well, just the thermal footprint would tell us what we need. But there are confusing noise sources. So, for example, clouds on the planet, volcanoes on the planet, geothermal sources as they rotate into view. Those will be hotter or colder than a signal from civilization. So we have to have multiple wavelengths. But see, that's the point. If they use power at all, the laws of physics tell us it has to be. No, it's based on the laws of physics, which are universal. Any source of power eventually gets converted to heat. That's the first law of thermodynamics. So it's unavoidable. Any civilization that uses energy has to produce heat. Laws of physics. Yeah. So the question was, and I'm sorry I forgot to reiterate the question, what happens if our search wants to emphasize the stars that are cooler? The stars that are cooler are also stars that live longer. I would turn that comment around. The stars that live longer are those that are more likely to show successful civilizations because they're older. The issue of what happens to a planet as convection in the core turns off, does that make the planet uninhabitable? I think I would answer that by saying that if a civilization can advance beyond our phase, I think it's quite likely that they could solve a minor problem like what happens in the core of their planet. But you're right, that's a question of the details of the civilization, and it's part of the reason why I think in making this debate, we're trying to stick with the laws of physics and those things that are unavoidable. And that may be a detail, which means that some fraction of that number of 38 times Fs is not detectable. And that's a good question to ask. We don't have any handles to try and answer it right now. Yeah. This is not a fundraising talk. I'm sorry. Okay. You could potentially take that energy and make Lego bricks and then convert that back into power you consume, but the power you consume will then be heat. And you can't, if your planet is at a temperature of 300 degrees, the best you can do is reintroduce that to the planet at that temperature. I'm not sure I understand or agree that you could convert your energy into Lego bricks, but we could talk about that offline. The question for the audience, again, was there are lots of effects that change the temperature of a planet. Is it really true that we have the power to extract this signal from all the other variability that affects a planet's temperature? And the answer is, it's probably true that in some cases we're not going to be clever enough to do that. The example that I showed you was an attempt at a blind reconstruction of a civilization signal that was 1% of the average temperature of the planet. And we extract that signal with very good fidelity. Now, it's an extraction that takes place with maybe a year of observations of a planet. So what Colossus will do is, of those 300 stars, spend a year visiting each one every night, capturing the signals from rotation, from the orbit, measuring the visible light and probably the infrared light in 2 different wavelengths. And the secret to extracting a signal due to civilization is to measure something that has a temperature close to the temperature of the planet, a little bit more as it rotates around the edge of the planet. Volcanoes don't have that. They're much hotter. We'll measure the temperature of that signal. The effect of clouds is to decrease the temperature in general, because clouds are higher up in the atmosphere. So the effect of clouds obscuring our vision is, again, to produce a noise source, and a noise source which would be cold rather than warm. You're absolutely right. A planet like Venus and a civilization that lives under a perpetual cloud cover, we won't be able to detect. So this isn't something that has a 100% success rate, but what I tried to demonstrate with some of those curves is that we can extract enough information to be able to make a case in, I think, most observations of extraterrestrial planets that may tell us about civilization. Yeah. This is not a fundraising talk. So it turns out that the world's largest telescopes, if you go back to the Yerkes telescope, which was a big lens 40 inches across, is all about the same in inflation-adjusted dollars, to within a factor of a few. The Palomar telescope, the 5-meter telescope, was a few $1 million when it was built. $6 million. Stan knows very well. The Keck telescope, when it was built, was, I think, about $60 million. Keck 1 was $60 million. The WLT projects that I showed you, the giant Magellan, the European Extreme Large Telescope, and what's the other one? The 30-meter telescope, are projected to be between $1 and $2 billion. That sounds like a lot of money, doesn't it? But it's not. It's the same price, inflation adjusted for inflation, as all of these other world's largest telescopes, which, by the way, were built with private money, not governmental money. This telescope, because it doesn't require a wide field of view, the Colossus Corporation wants to build for less than $1 billion, even though the diameter of the telescope is more than a factor of 2 larger than anything else that's being considered. So what happens is every night when it's clear, no. We look at the planet for 5 minutes. So we cycle through an observing program that captures these 300 stars, and the program is probably runs for 2 to 5 years to get all of the stars. And after 2 to 5 years, we've done our ETC census, down to an omega, which is something like 1% of the planet's thermal energy. So the question was a biological question. I'm not a biologist, but the comment is that the step from single cell to multi-cell life looks unlikely, takes a long time to happen, it seems. Life has been evolving on the Earth for billions of years. What if actually that was accidental? Well, if it was, then we're going to find out by doing this ETC census, and I'll be disappointed. In the back? So the comment is, if I could paraphrase, we're talking about applying the laws of physics in the standard Western literature. There are other ways of looking at life and existence and communication in the Eastern literature that involve action at a distance, consciousness, and other planes. Am I okay? And so your point, I think, is the fact that we haven't seen anything might be a test for us to evolve to another layer of communication ability and consciousness that really represents a transition. And that in fact is an interesting possibility. We don't have any handles on that as a scientist. Our approach and our group's fundamental interest in this problem is to try to learn something statistically about civilization and intelligence by finding thermodynamic signatures in our solar neighborhood. And that's a different approach. And you could very well be right that there's a very good reason that has to do with life reaches a point where it doesn't care about any of the questions or issues that we're talking about here. And that might be the answer. If it is, we'll do this experiment, and again, we'll find 0 or we'll find 38 from the census. Joe.
So I've had a discussion with a number of people about looking at possibly habitable planets around cool red stars. And so this calculation we have for FGK, have you
So the question was, if we think about stars that are very red, they're actually on this plot. So we've taken all the known stars within 60 light years we know pretty well. We know their colors, we know their temperatures, and we've taken them exactly to do what we're saying. So when we've computed how many extrasolar planets we could possibly see, and that's this plot, right? So this is a line that goes up just about like the diameter cubed that we talked about, right? As the diameter gets bigger, that number grows pretty fast. This is an exponential, a log scale, 1, 10, 100. The number here reflects the number of stars all the way down to the extreme cool end of the spectrum. So it reflects reality as we know it around us. Yeah, that was just a rough approximation to that exact graph that I showed you. And the numbers aren't so different. So that Drake-like equation that I gave you was to give you some idea of how the importance of the success of a civilization impacts the number of planets that we could detect with civilizations. And it's a pretty big number based on those assumptions that we're not too special. Okay. Thanks, everybody, for coming.